Hello, welcome to this first video in the series. The topic of this video is waves and particles. That might seem like a bit of an odd combination, but we'll realize that waves can be described as particles and vice versa. That's one of the fundamental insights of modern physics. We'll also describe the forces on those particles as we go through this, and these concepts will be very important for understanding the material that comes later in this series. So I will approach this in sort of a historical perspective. How the science was done, I think, is kind of interesting, and you learn a bit about the experiments along the way. So here we go. So we're going to start here with James Clerk Maxwell. In 1870, he described light as an electromagnetic wave, and it propagates through space like this. And what I'm drawing here are the electric fields. They change in space and time, and then perpendicular to that will be the magnetic fields. As the electric field changes, the magnetic field changes, and vice versa, and that propagates the wave through space. The wave propagates with a speed that we label c, the speed of light. In a vacuum, that speed is 3 times 10 to the 8 meters per second. The wave also has a wavelength. We label that with the Greek symbol lambda. And it also has a frequency, and we label that with the Greek symbol nu. Now, these three quantities are related to each other, so the speed, c, is equal to lambda times nu. So the wavelength of the light, or alternatively the frequency, controls what type of electromagnetic radiation you get. And here you'll see the visible part of the spectrum. It's a small part of the spectrum. It extends from 400 nanometers, blue, down to 700 nanometers, red. The longer the wavelength, the redder it'll be. At the very longest wavelength, you get microwaves and then radio waves. And then at shorter wavelengths, or higher frequencies, you get X-rays or gamma rays. So X-rays and gamma rays are just another type of electromagnetic radiation. All right, that brings us to the next stop on this historical tour. William Röntgen. He very famously discovered the X-ray in 1896. Here's the first X-ray that he produced. This is his wife's hand. We're going to talk a lot about X-rays in this series of videos and the text, but for now, we're going to just remember that light can be represented as a wave, and the speed is equal to the wavelength times the frequency. But it turns out that with X-rays, it's actually easier to talk about them in terms of the energy of the wave. So here the energy of the wave, or of a photon, the particle, is equal to the Planck's constant, h, which is just some number, times the frequency. So energy, we talk about energy instead of wavelength for X-rays, and we express it as electron volts. The energy that an electron gains when it moves through a voltage of 1 volt. For X-rays, typically it's kilo electron volts, 10 to the 3, or mega electron volts, 10 to the 6. Mega is 10 to the 6. So this is a rich area of physics, 1896 to 1897. We have Marie Curie, who discovered the effect of radioactivity, and we'll learn a lot more about her in the coming videos. And here we have J.J. Thomson, who discovered the electron in 1897. And then later in 1909, Robert Millikan and Harvey Fletcher did an experiment that showed that these charges were quantized, the electron charges. So they're discrete packets of charge, and they did this with this experiment here. This is the oil drop experiment. So the oil was vaporized, and each of the drops had an electron on it, and they could be suspended because there's a force pointing up in the field that balanced the force of gravity down, so they could float. So around this time, through some other experiments, it was possible to measure the charge-to-mass ratio of the electron. So then they kind of pinned down the nature of the electron. I'm not going to describe those experiments in detail, but basically what they did is to measure an electron moving in a magnetic field. And it's worth studying that because it illustrates some important physical principles. So here I'm going to draw the magnetic field. So this is the field pointing into the page. And then I'm going to come over here and draw an electron in red. And it's moving with some speed. V is moving to the right. Now, anytime a charged particle moves in a magnetic field like that, there's a force on the charged particle. And I'm going to draw it pointing up here. So it's some force F. So that force will act to bend or push the trajectory of the particle as it moves. So it kind of goes around in a curve, and it'll actually go around in a kind of a circle. Here I'm labeling the field, and the force, the charge Q times the speed times the magnetic field B. So at this point, a lot was known about the fundamental particles of nature. And I'm going to write them out here. You had the electron, and I'll write here the symbol E, and the charge is negative. You also had the positron. That's the anti-particle of the electron with the positive charge, same mass. That was discovered later. And then you had this positive thing in the nucleus, and I'll talk about in a minute, the proton, which was positively charged. Again, same charge as the electron, but the opposite sign. And then you had another particle in the nucleus called the neutron, N, and that doesn't have any charge. It's neutral. Then finally, now you have the photon, and that's written with the symbol gamma, and that's the particle nature of light. Again, it doesn't have a charge. It doesn't have a mass. To understand these particles further, it helps to understand the contribution of Einstein, and his theories tell us that the energy of a particle is related to the mass of that particle times the speed of light squared, equals mc squared. Anything that has a mass can also be said to have a rest energy. So here I'm going to tabulate the rest mass energy of these different particles. So for an electron, it's 0.511 MeV. For a positron, it has the same mass, 0.511 MeV. Mass and energy are interchangeable. The proton is much more massive, though, 938 MeV. And the neutron is more massive still, 939.9 MeV. And the photon, as I said, doesn't have mass. So I've been talking about waves and particles kind of interchangeably. And to really understand that, we need to talk about Louis de Broglie. In 1919, de Broglie postulated that matter can behave like a wave. And that sounds kind of crazy that a particle be a wave, but you can see that in experiments. You can do diffraction experiments, pass particles through slits, and you can find the wavelength of that matter wave. And it's given by the Planck constant h divided by the momentum p, the de Broglie wavelength. For particles, there's also the energy is related to the momentum through this equation. Energy equals momentum times speed of light. So I'm going to combine these two equations then. The de Broglie wavelength is equal to the Planck constant h times c divided by the energy. So the higher the energy of a particle, the shorter the de Broglie wavelength. So there's a lot more that can be said about de Broglie and his wavelength and other things in modern physics, but I'm going to leave it at that for this video. All right, I hope that was useful. I'm going to leave you with a little bit of further reading. I'll do this in the videos at the end to give you a bit more context for other references and so on. In the next video, we're going to get into the next scale of structure in terms of size, so the atom and how that is structured. We'll see you in the next video.